Okay, so here's an example of a question involving forced oscillation, so forced harmonic motion, if you like. And it's this question 6 I'm talking about. So the particle is attached to the end of a light elastic spring, which spring is oscillating. So the end of the spring is oscillating itself, and then the particle is oscillating as well as that. So all we've got to do is just find x as a function of t. So really, well, what I'm proposing here is that you just solve the differential equation, and you know, when there's a question that involves damped harmonic motion, forced harmonic motion, simple harmonic motion, if you can just solve the differential equation, then you know that's all you're really after, and then interpreting the answer and everything is another step, and we'll look at that in a future video. Like, but let's have a look at this. So this differential equation then, d2x dt squared plus 9x equals k cos t. Now it's not a very difficult equation to solve. The complementary function is just so. Oh yeah, I haven't said this, have I? It's got a right hand side where there's a function in it, so we'll have to sort that out with a particular integral. But firstly, let's look at the complementary function, which is obviously dead easy. Just d2x t squared plus 9x equals 0. Yes, let's solve that. Should we just go straight to it? Yes. Okay. X equals a cos 3t plus b sine 3t. Nice one. That's fine. Happy with that. Okay, the particular integral then. So we're going to try what? So try. My writing's a bit messy here. Try x equals, there's that there, k cos t. I'm going to try lambda sine t plus mu cos t, and we'll see what lambda and mu are. Okay, so differentiate then. Dx per dt is what? Lambda cos t minus mu sine t. And what about d2x per dt squared? There we go. Minus lambda sine t minus mu cos t. Okay. Now, what are we doing? We're subbing these into the original, aren't we? So, let's do it. Minus lambda sine t minus mu cos t plus 9 lambda sine t plus 9 mu cos t equals k cos t. Okay, I think I'm going to run out of space here. What have we got there then? Let's tidy this up. Let's, what's the word? Not evaluate. Oh, what's the word? Equate the coefficients of cos t on the left hand side and the right hand side. But 8 mu cos t equals k. Well, that's good. K equals mu equals 8. Mu equals k over 8. Okay. And equate coefficients of sine t. What have we got? 8 lambda sine t equals 0. 8 lambda is 0, so lambda is 0. So that tells us the particular integral is, well, the whole, not the particular integral, the whole function is x equals a cos 3t plus b sine 3t plus k over 8 cos t. So that's that there. Okay, we've got, oh sorry, I went off the screen there, but we've got mu is k over 8, so that's our particular integral is x equals k over 8 cos t. So plus k over 8 cos t. Okay, that's it really. We need to work out what a and b are. So I'm going to differentiate this and say dx dt is, I'm differentiating this, minus 3a sine 3t plus 3b cos 3t, and then differentiate this minus k over 8 sine t. Oh, the way I went quiet then when it was having to think about me pluses and minuses. Right, okay, so in the question, what's it say? It says when t equals 0, x equals 0, and dx dt is k over 5. Okay, So t equals 0, x equals 0. That tells us that on this here, 0 equals a. That's 0 plus k over 8. A plus k over 8. Well, that's nice. So a equals minus k over 8. Okay, and when t equals 0, x equals e. So dx over dt equals k over 5. So we've got k over 5 equals, I'm looking over here, 0 anyway, plus 3b minus 0. So 3b. So b equals k over 15. Okay, right, so that's the answer. And I'm done. X equals k over 15 sine 3t minus k over 8 cos 3t plus k over 8 cos t. Now, right, I'm going to say two really conflicting things now. Firstly, what have we just done there? We've just solved a differential equation. Basically, we've solved this differential equation here to get this solution. Right. Oh, it's gone off the screen. I'm pointing at it in the meeting. Right, we solved this differential equation to get this solution. And then we subbed in the initial conditions here to find out A and B. So there's the solution there. That's all we've done. That's all we've done there, is solve the differential equation. But it's absolutely crucial that we consider the context of this. So the context of this is that we've got an oscillating particle on an oscillating spring. And that's the mad thing. And the oscillating particle, the natural frequency of that is this here. Whereas the spring is oscillating with the frequency that gives us this. And it's really interesting how those two knit together in the solution here. Now, it would be interesting for you to go and draw that yourself. So, you know, I showed you, didn't I, how to draw it on autograph. I say it's interesting. This actually has quite an underwhelming graph, really. So the actual graph of this looks like doesn't really show the underlying pattern of what's going on. But it is a really interesting situation when we've got two different arguments there. So there's this. We could put this together all day into one sine or cos function, but this is a nuisance because it's got a different argument. So therefore, it's going at a different frequency. So that makes it completely different to anything we've seen before. And I'm going to talk about that in the future, and it is really interesting. But don't forget that if you're unsure of how to do any of these, you just go back to solving the differential equation. That is the sort of differential equation that actually is bread and butter to us. So if we can solve that and get that solution, that's the end of the question. Like, no, make no bones about that. The rest of it, what might say there's nothing else like, but the rest of the question might say, oh, what's the behaviour of this as t tends to infinity? And well, this one just keeps oscillating, to be honest. But you know, we've seen that before with damped harmonic motion, haven't we? Where, you know, stuff decays away or whatever. But it is really important that there's two things going on here that I'm saying that it's different. So firstly, solve that equation to get that, fine. But equally, be aware of the context and be aware of that this here is actually very, very different to something that we've seen before. Okay, well,